Hello everyone. In this video, we will explore the relation between kinetic energy and work, which is known as work-energy theorem or the principle of work and kinetic energy. By the end of this video, we will gain a clear understanding of this theorem and its underlying principles. To kick things off, a solid grasp of Newton's second law is essential. Okay, Newton's second law is one of the most important laws in all physics. This law, which is a quantitative description of how forces change an object's state of motion, states that the acceleration of an object is directly proportional to the net external force applied to it, and inversely proportional to its mass. Mathematically expressed as F equals to m times a, where F represents the net force acting on the object, m is its mass, and a is the resulting acceleration. This law emphasizes that the change in motion of an object is directly related to the strength of the force applied to it and how much inertia it has due to its mass. According to this law, if a body has a net force acting on it, it is accelerated. Conversely, if a body is not accelerated, there is no net force acting on it. Following this equation, it is obvious that a larger net force acting on an object causes a larger acceleration. And objects with larger mass require more force to accelerate. In other words, more force generates more acceleration for a given mass. On the other hand, more mass means less acceleration from a given force. After achieving a firm understanding of Newton's second law, it is important to learn about the concept of work. What is work in physics? Work is energy transferred to or from an object by means of a force acting on the object. It is important to mention that work can be positive or negative. If energy is transferred to the object, work is positive, and we can say that the force applied to the object is in the same direction as the displacement of the object. On the other hand, if energy transferred from the object, work is negative. In other words, force applied to the object is in the opposite direction to the displacement. For example, let's take a look at this picture. Here, we have a box that force F is acting on it. Obviously, the energy is transferred to the box by applying an external force F. And the force applied is in the same direction as the displacement of the object, which is in this direction. So the work here is positive. The question here is how we can calculate the work. The work done by a constant force on a particle during the displacement d is mathematically calculated using this formula. F times d times cosine of the phi, where F is the magnitude of the force applied to move the object, d is the distance the object moves in the direction of the applied force, and phi is the angle between the direction of the force and the object's movement. There are two important points here to clarify. First point is that the force should be constant. The This means it must not change in magnitude or direction as the object moves. In the case of variable force, there is a need for integration, which is out of the scope of this video. And the second matter is that the object should be particle-like, which means that the object must be rigid and all parts of it must move together with the same behavior and in the same direction. Work is essentially about using force to make something move. Just imagine pushing a box across the floor. If you push it harder or for a longer distance, you're doing more work. If you're pushing at an angle, only the part of your force that is actually moving the box counts as work. The other important concept you should learn about is kinetic energy. Kinetic energy, denoted by K, is connected to how an object is moving and is the energy an object possesses due to its motion. The faster an object moves and the more mass it has, the more kinetic energy it has. In simple terms, the equation for kinetic energy is 1/2 times m times v squared. Here, K is the kinetic energy of the object. M represents the mass of the object, and V is the velocity of the object. The equation reveals that kinetic energy is directly proportional to both the mass and the square of the velocity of the object. This means that either the mass or the velocity increases, the kinetic energy will increase as well. Moreover, the relationship between kinetic energy and velocity is particularly noteworthy because the velocity is squared in the formula. This means even a small increase in velocity can lead to a significant increase in kinetic energy. Based on this connection, when an object is stationary, it's not moving, its kinetic energy is zero because of its velocity is zero. And as the object starts to move and gains speed, its kinetic energy increases proportionally to its velocity and mass. Think about a ball rolling down a hill. As it gains speed, its kinetic energy increases. Now, when this ball hits another object, the kinetic energy is transferred to the object, causing the objects to move, deform, or break. Now, we are ready to talk about work-energy theorem. Let's consider this cubic box that can move along a frictionless surface that is stretched along a horizontal axis, and use it to better understand the equations related to this theorem. As we can see, a constant force F directed at an angle phi to the surface accelerates the box along the surface. According to Newton's second law of motion, this is how the force and the acceleration along the x-axis are related. F in the direction of x equals to m mass times acceleration in the direction of x. Let's keep this equation here. On the other hand, about the motion of a particle with constant acceleration, we know that the velocity of the object at any point from the start of the movement is calculated as follows. Vf equals to V0 plus a times t. If we raise this equation to the power of 2, the equation 2 is obtained, and we will use that later. As we know, the average speed is determined by dividing the total distance traveled by the amount of time taken for the movement. By utilizing this equation, we can derive equation 3. Due to the constant acceleration of movement and the linear function of velocity mentioned in equation 1, the mean speed within each time interval corresponds to the average of the velocity at the beginning of the interval, which is v0, and the velocity at the end of it, which is vf. It is shown in equation 4. Combining equation 1 and 4, we arrive at equation 5. It shows the relation of average speed with initial velocity, acceleration, and time. By utilizing equation 5 in conjunction with the derived equation 3, we can easily arrive at equation 6, as it is shown. Subsequently, using equation 7, we can form a significant correlation that connects acceleration with initial and final velocity and distance. The equation W equals to F times D represents the work done on an object by a force F over a distance D. By applying Newton's second law, we can substitute F in the equation. Now, using the previous equation of acceleration, we get kF minus k0. This equation is known as the work-energy theorem. It demonstrates how the work done on an object is related to the change in its kinetic energy. The net work on an object is equal to the object's final kinetic energy minus the initial kinetic energy. Also, it is considerable that the work-energy theorem applies to the net work, not the work done by a single source. Also, when an object is experiencing the influence of two or more forces, their net work is the sum of the individual works done by each force, which is also equal to the work that would be done on the object by the net force of those forces, F net. Let's consider this cubic box as an example to get a better understanding of the work-energy theorem. In this given scenario, the applied force, denoted as F here, doesn't align directly with the object's displacement along the x-axis. Rather, it acts at an angle phi in relation to the displacement d. It's crucial to recognize that for work to occur, the force and displacement should be parallel. Therefore, it is only horizontal component of force F that does the work and initiates motion along the x-axis. The component mentioned earlier, F cosine of phi, initiates the object's movement, propelling it with a small initial velocity. So its kinetic energy is small too. At this stage, the cubic box has an initial kinetic energy of 1 over 2 times m times v0 squared, referred to as k0. As long as the object continues its forward motion, the object velocity undergoes transformation, so the kinetic energy changes too. At the end point of the movement, characterized by a displacement d, the velocity transforms into vf, representing the final velocity. Consequently, the kinetic energy at this particular point is equal to Kf equal to 1 over 2 times m times Vf squared, denoting the final kinetic energy, which surpasses the initial kinetic energy due to the greater velocity. According to the work energy theorem, the force F accomplishes work computed as F times D times cosine of phi, leading to a transition in the object's kinetic energy from K0 to Kf as the object moves and changes its velocity. Notably, this force performs positive work on the object, amplifying its speed and kinetic energy. After displacement d, the work denoted as W carried out by force F along the x-axis equates to the change in the object's kinetic energy, showing the transition from the initial point of movement to the ultimate point symbolized as delta K. Now, let's recap the key takeaways from this video. First, we talked about Newton's second law. As it's shown in this equation, this law states that the acceleration of an object is directly proportional to the net external force applied to it and inversely proportional to its mass. After that, we explored the concept of work, which is the energy transferred to or from an object through the application of force. And we showed that it is dependent on the magnitude of the force, the distance the object travels, and the angle between the direction of the force and the object's movement. Then, our exploration brought us to the concept of kinetic energy. This type of energy arises from an object's motion. This equation reveals that kinetic energy escalates in direction proportional to the object's mass and the square of its velocity. Ultimately, using these foundational concepts, we arrived at our primary goal, which was understanding the work energy theorem. This theorem states that the net work exerted on an object is equal to the difference between the object's final kinetic energy and its initial kinetic energy. We proved that through mathematical calculations and the application of basics in physics principles. We came to the end of this video. I hope that this video has provided valuable insights and expanded your knowledge.